Let's suppose you have a mass, and then you are going to lift it with some force. Or let's suppose you are going to push, for example, your luggage on a horizontal table or on the ground. If you move the object certain distance alongside the force you are applying, there is this concept of work. Work is a scalar magnitude which relates the force applied to an object and how much you move the object from one position to another position. So in general, you will have a path like that, and then let's say you are moving an object from here to here. If you know the length of all that, we can say, so let's say you have this going a distance h, and this moving a distance delta x. The general equation for work is F multiplied by delta x. Now, let's look in terms of a scalar. I mean, when you multiply two vectors, you get a scalar, but here, the scalar definition of work is equal to force and distance, all right? So it's force and distance. Force times distance. And now is when we can start relating forces. We can start relating energy. Many examples are of those. Imagine when you have a hammer and you want to remove a nail. And that's an example that you have on the slides. Or when you want to lift a mass on a ramp. That's actually a good one. We have a ramp. And again, we are going to disregard friction. So we are going to just talk about the mass there. And then you have a force acting on a body. If that's the case, you will say that the work is equal to this force and this distance. But guess what? When you lift a mass across the plane, that force is not the only one doing work, because you have the plane also reaching some height. And you know already from the previous chapter in the forces diagram that there is something called here mass times gravity. So there is a force due to this. The force is moving it parallel to the plane. So there are different works. One is the work by the force, which is force times distance. That's the equation, by the way. And the other one is the force due to gravity. The force due to gravity is mg times h. We're assuming that it started from the bottom, all right? If there is friction, there is also work due to a friction, by the way. It all depends on the force acting and the distance traveled. Units for force. The unit for work. The unit for force is Newton. The unit for distance is meters. So Newtons times meters, which we call, so now we have a new set of units, joules. So this is newtons times meters, they together give you what? Joules. So put here J, joules. And the problems are not that complicated. You could have a situation where you have angles, like in the ramp. Or if I give you, for example, the force not acting like that, or like that, but I can give you a situation where you have a force acting on the same mass. And you know what's the thing? This proves why you want to carry luggage always making an angle like this. It's easy, besides the wheels. And I want to show you with the physics here. If you have a force acting like this, the work that you are going to do is not just force times whatever distance. So let's say this moves a distance here, d. It's not F times d, because now there is an angle. So now you probably remember, if force is a vector, we can find the what? We can find the components of that vector. Right? Here, we can find the y component and the x component. The x component is F cosine theta. The fact that you have cosine theta makes the value of the force less. Cosine is always less than 1. Alright, in that case. That means that it's less than the force, so the work here, so this is the general equation, but in this particular case, the work is F cosine theta times distance. So less work than there. Less work. Even though you use the same force. And you move it the same distance. That's because of the angle. So whenever you guys are pulling or pushing something, that's why we use ramps. There is this joke that when you push something across a ladder, right? If you have a very big, let's say, desk or a piece of furniture, if you put it on a ramp, then remember, right? That was the original idea that was believed the Egyptians used to build the pyramids. Now we know it's not. It wasn't like that. It was something more like a ramp going inside the pyramid, and they were doing it alongside the construction because we never found evidences of a big ramp, but that would be an alternative, but that will take a long time to bring those big blocks across the ramp. So the ramp, if it's like that, depending on the angle, right, it gets easier to move. But as the ramp goes into a higher angle, it's more complicated, right? It gets steeper, so you require more force. All right. Let's show the slides now. There's the equation for work, and that's an example there. 100 times 300 newtons meters, or 300 joules. Okay. Let's see this. Let's say you have a barrel in the figure that has a mass of 30 kilograms, and at the height of the dock, so you're on a dock. They give you the height, right? And they ask you how much work will you do when lifting the barrel. So you are not moving the barrel across the ramp. You are lifting it, right? So look at what I just illustrated, right? If you use a ramp, you can travel twice the distance with the same force, and you will get the same work, 2 times F times D, right? But if you want to lift the barrel, right, you will have to apply double the force for half the distance for just D. All right. You will produce, you will have, yeah, you will have the same work in both cases, but with the same work you will actually be able to lift or to move the barrel up, right, with less amount of effort. That's because we calculate the weight of the barrel and then multiply that by the distance, 1.2. That's the height of the dock. But if we calibrate, we make a ramp big enough, we can do the same amount of work, right? And yes, we will travel more distance, but the force that you will use will be less. Okay? So there you are, that's a good example there. Now, be careful with situations like that. If you already lift a mass and you move with that mass, for example, let's say you lift your bag, all right? Look, you are sitting in a classroom and then it's time to go, right? You lift your bag, you are doing work, right? Because you're doing work against gravity, right? Or the weight of the bag is what you are carrying, that's the force you are exerting. Once you put it in your bag and then you start walking with it, you are not doing work. Because now the system is in equilibrium with you. It's not moving anymore. It's you with the bag moving. So in that picture, when the kid is moving with the box, right? He did work when he lifted. Once he starts walking, no more work. All right. Another situation is when, let's say, you are pushing towards a wall, and the wall is not moving. There is also no work in that case. And there is no work because the wall is not moving. It doesn't matter how much effort. It might seem like you're doing a lot of effort, right? Like pushing it, but no. So if you're in the gym, for example, right, you do work when you lift. But if you are carrying, I mean, you are doing some exercise, but let's say you're moving weights from one place to another. Once you lift them, that was a work. All right. So just for you guys to know, okay. Now, how come work is not a vector? Because there is no direction associated with work. But we can have negative work. That's one of those concepts or quantities that are very particular. And let me show you when you can have negative work. All right. We will do that in energy. Doesn't mean that we have negative energy, because energy is the ability to do work. We're getting towards that. There is no negative energy, well, as far as we know. But there is negative work. It's more like a concept, more like a quantity. Right? A quantity, we can always take the absolute value and say, yeah, it's positive. But what happens about, or how can we get negative work? When this force is pushing you to a right, and you're probably thinking when you go to a left, sort of. Let's suppose you have a body moving against friction. That's when you can have negative work. When the force is opposite to the overall direction of motion. So, if you have an overall force, all right, and this mass, remember, mu. That mu means that there is friction, all right? The coefficient of friction can be static. In this case, we want to use the kinetic friction. So we know there is mg, there is the normal, which, by the way, you only have normal if the object is on the floor. In that question in the exam, when there was a mass that was on the air, like that, this mass right now doesn't have any normal. There's no surface, right? However, if I push it towards the, okay, here. If I push it towards here, there is normal. The normal is acting from the whiteboard towards this mass. All right. So make sure that that's clear. All right. Let's see. Okay. So pretty much, let's now introduce the idea of negative work. You can have a situation where the work, you do work with a force acting like this, but you know there is a friction. Friction is mu times normal, right? Anyway, you just draw it towards the other direction. That's friction. But force overcomes friction, so it travels a distance d. You can say that the work done by the force is force times distance, but the work done by the friction is minus the force of friction times the same distance. So there is negative work. All right. Then always when there is friction, friction is a non-conservative force. That's why. The force of gravity is conservative. So that's that. All right. Let's see. Let's see this question. Okay, let's do this. Work is done on an object when what? It moves in a circle, is accelerated in a straight line, is carried horizontally, all of the above. What do you think?
I will say 4 because for all of them there is movement.
Yeah, but what did I say about carrying? When you carry something, is that work? The example?
No, no,
No.
exactly. Yeah.
So in that case, guys, it's only 2 because also in a circle, there is no work, all right? When you are in a constant speed, there is centripetal acceleration, but there is no change on velocity. There is no change on mode on. There is nothing to produce work in that case. Work is done when you accelerate something in a straight line. All right, vertically or horizontally. All right, so there has to be a force. If there is a force, there is acceleration. Then you can have work. So that's number 2. All right. Okay, what do you think about this? If a force acting on an object and the object's velocity are in opposite directions, the work done by the force is what? Positive or negative?
Negative.
Negative, exactly. Let's talk about that. True or false? The force of gravity cannot do work.
False because there is gravity.
Yeah, exactly. And if you push something up or pull it up, there is force of gravity. Very good. Force and distance. So now, how relevant is the concept of work? A lot. There is work when we talk about electric charges, when we talk about magnetic fields, when we talk about mechanical work, right? When we push something, when we lift something. But we need to find a way to measure it, guys. When you guys go to the gym, in the treadmill or in the bicycle, stationary, they don't give you how much work you are doing. What can you read in the screen? What do you guys read when you guys go to the gym and you see the thing in there? Or, okay, you guys have a smartwatch, right? At least one of you. You count your steps. Why do you count your steps? What's happening after you reach your limit or your goal? You have burned what? When you see on the screen in the gym, when you use a smartwatch, you burn calories. And calorie is also a unit of work. But technically speaking, calorie is a unit of energy. So you are using energy. All right? Now, that's the way we measure a system's ability to do work. All right? And yes, this is normally transferred when work is done. If there are only conservative forces acting on a system, we have the conservation of energy. That's the other conservation law. All right, the idea that energy is neither created nor destroyed. It's only transformed. Conservation of mass, conservation of charge later, conservation of momentum, we talk about it, and now conservation of energy. Now, work is done when a ball is thrown, right? You do work when you accelerate the ball, for example, but also when you catch it, right? There's a work done on your hand due to the force that you feel to stop it, right? When you are driving a car, another example of negative work, by the way, and you press the brake and the car stops. What's making the car stop is an action that you are inputting towards the car engine. But there is something called a braking force. That force is opposite to the motion of the car times the distance that you travel since you press the brake. That is the work done by the brake of the force, by the braking force. All right. When work is done on something, right? For example, if you push it or if you are trying to stop it, it's gaining some energy. So you are giving energy to the car to stop it. That's why we don't talk about negative energy, but we talk about negative work. The work is negative, but the energy is gained by the system. All right? And the energy is used to do that work. That's the whole idea of conservation. All right? There, right? When we lift an airplane, when we lift a box, when we try to stop a car. So, what are the different types of energy? You have talked about energy before in physical science, in school, maybe even in chemistry, but there are different kinds of energy. There's heat, there is energy of the sound. The most common type of energy, guys, is this, the kinetic energy. In mechanics, that's the most common one because that's the one that is related to the speed of an object. All right. When the object is moving, we have the KE, kinetic energy. Right? It's very simple to compute it if you know the speed and the mass. The usage of it is what matters. And you will see that we're going to use it a lot in conservation laws. For example, guys, and we're going to go ahead a little bit, but when you have, and you probably have heard about this, you have a roller coaster. I'm sure many of you have been in a roller coaster before. So there is a moment when the roller coaster is going, remember we talked about the force of gravity and your stomach going up? Okay, that's the whole idea behind forces and the centripetal force on the loop, right? But as the cart is going up and is building tension, right? Up, 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 is gaining some sort of energy that we're going to talk in a little bit. As it reaches the top of the loop or the ramp, and then it drops you from like what 100 meters, right? Maybe even more. You feel your stomach going up, but that's because the car is gaining a lot of speed. at the bottom of the ramp, the kinetic energy is the maximum. But where did the kinetic energy come from? From the fact that it was very high. The higher you are, the higher the speed is at the bottom. So yes, you can calculate the kinetic energy, right, using the equation. But the main idea, guys, behind energy is how it's conserved. So let's talk about not just kinetic energy, but let's talk a little bit about let's talk about potential energy. So the two most common types of energy in mechanics: kinetic energy and potential energy. All right? I'm going to draw the diagram on the board I was talking about. And actually, that brings the most common example and lab that you can do when you have a roller coaster. So let's say you have point A, and then you have something like this, and then going like that, like that. So, like that. This is point A, point B, point C, and we have a mass here. And it's at rest. When it's at the top, when it's reaching the top, right, normally it's almost at rest. Still moving a little bit, but we are going to assume there that it's at rest. The first thing we need to do is to write down the energies that we use in mechanics, the most common ones. Kinetic energy, Ke, which is equal to 1/2 mv squared. And remember, energy is the ability to do work. If work is related to energy as a measurement for work, it has the same units. So, joules. Right? Good. But we also have an energy related with the force of gravity. We know that, and you answered that in the previous question, right? The force of gravity, the weight, exerts some work when you lift it, for example, right? Or when you push it along a ramp. So let's prove it. If you have a mass here, and then you lift it to some height, let's call this H. The only force that was acting, or sorry, not the only force. The force of gravity was acting always down. So the work done by gravity is equal to the force times distance. Now, technically it should be negative, but we're going to assume, we're going to just care about the magnitude. That's the equation for potential energy. The gravitational potential energy, or in some textbooks, sorry, they call it the gravitational potential energy. I don't like to call it like that, and many textbooks, they don't do it, because you can get confused with the gravitational potential energy of planets, which has another equation. It's similar, but remember that there's an equation for gravity that we did, right? At the end of chapter 2, we prove, actually, that gravity can be written as G mass of the planet divided by r squared. And then if we multiply by m and by height, and we assume that we are on the surface, that's the energy of a planet, gmm over r. But that's different. All right? For now, we want to say that potential energy respect to the ground, that's important. The potential energy is equal to H, but you need a reference. And your reference is always the ground. Guys, I think for this particular chapter, the notes are gonna be very useful. So at the end of the class, of time, I will show you the notes that I think you should either print or summarize. That could be sort of like a homework for the weekend. For chapter 1 and 2, I think it was just okay. But for this chapter, I think it would be a good idea because those notes are very well summarized. And even though it has some examples there that might be a little bit, and we will try to do them actually next class, they do have a nice summary of all this. Kinetic energy, potential energy, and then the other one that we want to talk about later. But now we know that there is a potential energy depending on where, how high you are. So this pen here, if I lift it, has more potential energy than this here, right? Remember, uh, we remember that we want to always have a reference. The reference is normally the ground, but not always, right? This is the easiest reference to take, like the surface of the earth. So every object right now, where we are, we have zero potential energy because we're on the surface of the earth. As you go up, a plane, a helicopter, or whatever, a balloon, they start gaining potential energy. And that's what happens here. When this guy is there, it gains potential energy because it's very high. But then, as he goes all the way down, is losing potential energy. But we know that energy is not lost. It's transformed into what? In this case, kinetic energy. Since there's no friction and it's only the gravity, the force of gravity acting in there, we can finally say that that's a conservation of energy. So the other conservational law will be the conservation of energy. Conservation of energy. And the nice thing about this is that it allows you to solve many applications and to explain many things in life. Now, in a roller coaster, there is friction and there are other factors. But when we build a roller coaster, one of the parameters to know how high, how fast, and the way the rails are going to be shaped is the mechanical factors, right? So we have here an altitude, and obviously here, so this is your reference. We call this the ref. When the ball travels without friction and reaches this point, it has a velocity. The magnitude of velocity is speed. So what does the conservation of energy tell us? That the energy on A is equal to the energy on B equals to the energy on C. So then this one is put here, H2, H1. Then, now, we already have introduced the idea of kinetic and potential energy. But I put there energy. So something I want you guys to know is that there is a parameter that we can use in physics, which is called mechanical energy, which is basically that. The mechanical energy of a system is the addition of kinetic plus potential energy. We use that also in heat, thermodynamics, and other branches of physics. But I think it's okay if I erase this. And here, let's write the equations that we have already. potential energy mgh, and then we're gonna call E the mechanical energy, which is the addition, the sum of potential energy plus kinetic energy at any point, right? So clearly, the mechanical energy here is just the potential energy, mgh. And here, the mechanical energy will just be the kinetic energy, right? All right, guys, I think it's a good point to just now show you the notes that I want you guys to read. You can already start doing the homework, by the way. We covered a lot of concepts today, so that's good. Yeah, so the other thing that is left will be to talk a little bit more about potential energy, to do a few examples, solve some problems, and then talk about potential elastic energy. Let's see, conservation of energy, energy conservation. Yeah, that's the idea behind. Yeah, awesome. And then do problems on collisions as well. So let me show you what I want you guys to read. Wait, I have to close this and then show you guys this. So I think what you guys should go today, so recordings, slides, we're doing this. There will be another one this week. Wait, this is, yeah, we'll put the energy problems and work in there. The notes. Going to energy notes. You can take a look at these two as well. That's momentum and impulse. But I like these ones in particular because look, it has everything we talk about. Mechanical, work, an example there of work, kinetic energy, potential energy. So I like this. It's pretty good. There's a few animations in there. And then we'll start talking about springs again next class. All right. So take a look at these notes, guys, and start working on the homework. I wouldn't worry about the grades. I think the grades are pretty good. We will have a quiz on chapter 3. I will let you guys know probably again on a Tuesday. I don't think it will be next Thursday, or we'll see. I'll let you guys know on the weekend. We might be able to have it on Thursday because I want to have the exam after Columbus Day, on the 15th. Maybe the latest this day, but probably a good idea to have it this way. So I think we'll have a quiz on the 8th, guys. Whatever we do on Tuesday, all right, that will be the quiz on Thursday, and then we can go and do a review, total review, after Columbus Day on Tuesday the 13th, okay? So it won't be a long quiz. It'll be a short quiz on the 8th, and then we can start doing the review, finish the chapter, doing the review, or probably we'll have done the chapter already. I think we'll finish the chapter by this on the 6th, though. So we can have a quiz on the 8th, and then, guys, on this Tuesday, we'll do a review, so make sure you're here, and remind me to record the lesson, okay? And then on 15, we have a first exam. The first exam, if you don't mind, I want to start the first exam this day. I will say the earliest will be probably 3:15, okay? And then we can go up until, if you need, till 5, because it's 3 chapters, and you may need some extra time, all right? Are there any questions?